Hello, everyone. It is my pleasure to present our work, ORCA, a benchmark for object recognition and comprehension for archiving marine species. While the ocean covers over 70% of our planet, it remains a mysterious abyssal region in the world of computer vision. While terrestrial AI has seen explosive growth, marine visual understanding has lagged behind. This isn't just a technical gap. It's a critical bottleneck for marine biology and ecosystem protection. ORCA was designed to bridge this gap by providing a large-scale, multimodal dataset for marine research. Current marine AI faces two primary hurdles. First is the lack of data diversity. Most existing datasets are geographically limited or restricted to a few categories, which means they often focus solely on local group of species community. This narrow scope prevents models from generalizing across the vast taxonomic breadth of the ocean. Second is a flaw in task formulation, where some of the widely adopted computer vision tasks do not necessarily tackle the marine-specific requirements. For example, datasets rely on image-level classification or coarse labels. But, in the wild, a single image often contains multiple species interacting in complex ways. On the other hand, image captioning lacks the fine-grained perception to generate detailed documentation. Simple captions like, "There is a turtle," are insufficient for biological surveys, which require a deep understanding of specific morphological traits, behaviors, and habitats. To address these gaps, ORCA introduces three key pillars. First, broad taxonomic coverage, spanning hundreds of species to ensure ecological depth. Second, instance-level annotations, providing the fine-grained perception needed to localize species in cluttered environments. And third, biology-oriented captions, which offer expert-verified descriptions of physical traits and behaviors. By integrating these, ORCA supports three critical tasks: object detection with both closed set and open vocabulary setting, visual grounding, and instance captioning. These tasks allow us to move beyond simple identification toward a structured, biologically meaningful archiving of marine data. More importantly, ORCA analyzes how morphological overlapping affects the localization and identification of species. Species belonging to the same higher-level taxonomic groups, such as the same genus or family, tend to share nearly identical physical appearances. This high degree of visual similarity makes distinguishing between them a significant challenge for standard AI models. ORCA tests whether models can move beyond general silhouettes to identify the subtle, distinguishing features required for accurate species-level classification. Building ORCA required a rigorous, multi-stage pipeline. We began by using GPT-4 to generate a comprehensive list of marine common names, which guided our image curation from global platforms. Once the imagery was collected, we manually annotated bounding boxes for every observable species. For each region, we used Marine GPT to generate initial descriptive captions. The most vital step, however, was expert verification. Marine biologists reviewed every caption, labeling them as positive or negative based on scientific accuracy. Experts are also encouraged to refine the caption to provide professional caption annotation. The result of this effort is a benchmark dataset with over 14,000 images covering 478 species and 670 common name categories. What truly sets ORCA apart is its granularity. With over 42,000 bounding boxes and 22,000 expert-verified captions, we provide a level of detail far beyond standard web alt text, which is too brief for documentation or other biological applications. We also retain the negative captions for analyzing the cause of failure. Unlike other datasets that focus on either just vision or just text, ORCA maintains a strict balance between both modalities, which enable ORCA support wide range of multi-model tasks. Furthermore, ORCA provides a dense and diverse caption annotation, where the caption token length is significantly longer than other general and marine-specific dataset. This is the first marine dataset to provide dense, diverse, and instance-level captions that capture the specialized knowledge required for marine science. With the dataset established, we benchmarked 18 state-of-the-art models across our three core tasks. To specifically measure the impact of morphological overlap, we introduced three evaluation settings: class level, intraclass, and interclass. At the class level, we group organism by their board taxonomic class category, where the same class category usually share similar physical appearance. In the intra and inter settings, we adopt a more granular approach that we group organism by their taxonomy species category, creating a more challenging setting because even some organisms share similar appearance. They may have different species category. For our open vocabulary and grounding experiments, we randomly sample categories to be seen or unseen except for interclass, where we adopt a leave one out approach, where we define one category as unseen for every 4 categories which belong to the same taxonomic class. Looking at the detection results, a clear trend emerges. Most models perform best at the class level, where visual patterns are broader and easier to capture. However, performance drops significantly at the intraclass and interclass levels. This confirms that the majority of current detection models struggle with morphological overlapping. They can see an object, but they can't precisely identify the species when visual cues are subtle. One notable exception was Decola, which showed a clear advantage. We attribute its success to its language-conditioned query selection, which better aligns visual features with specific linguistic labels. In the visual grounding task, we provided the models with a descriptive caption and asked them to locate the corresponding object. Interestingly, we found that performance remained consistent across all taxonomic levels. This suggests that detailed captions act as a powerful anchor, helping models overcome the confusion caused by morphological overlapping. Furthermore, our results show that fine-tuning on ORCA significantly boosts a model's zero-shot grounding capabilities for unseen marine species, proving the value of our domain-specific data. Finally, we evaluated instance captioning. We tested models on both image-level and region-level descriptions. We found 2 major takeaways. First, models trained on generic datasets tend to produce very brief, common-sense captions. ORCA's dense, expert-verified captions are essential for training models to be more professional and descriptive. Second, while models are decent at generating image-level caption, they struggle to capture fine-grained region-level features for captioning, where the scores significant drop from image-level setting to region-level setting. This highlights a significant gap. General-purpose captioning models are currently not equipped for the specialized demands of marine biology without the kind of targeted supervision ORCA provides. In conclusion, ORCA establishes a new comprehensive benchmark for the marine domain. By providing the first large-scale dataset that unites object recognition with detailed visual understanding, we have created a foundation for the next generation of multimodal marine AI. Our evaluation highlights both the strengths of current models and the urgent need for domain-specific algorithms. We hope ORCA will serve as a foundation for future research, ultimately aiding in the vital mission of monitoring and protecting our oceans. Thank you.